Is Alex Margolis from Vanderbilt University, and today we'll talk about modal geometries dominated by locally finite graphs. Please.
So thanks very much for the invitation. It's a pleasure to speak at this seminar. Yeah, I'm going to talk about model geometries dominated by locally finite graphs, which informally you can think of this as saying, this sort of says which finitely generated groups have the property that the only spaces they act on nicely are essentially locally finite graphs. So goal of geometric group theory, hopefully this shouldn't be too controversial, is that we want to study a finitely generated group gamma using its actions on metric spaces. And we want to deduce algebraic properties about the group gamma from geometric properties of spaces on which it acts. And every group acts trivially on every metric space, so we need to put some assumptions in order to make any progress. And we have the following definition. So a model geometry of a finitely generated group gamma is a proper metric space X, which admits a co-compact proper isometric action of the group gamma. And there are quite a few words here, and most people hopefully know what they are, but I'm just going to define them so we're all on the same page. So a proper metric space is one where closed balls are compact, and an action is co-compact if there's some compact subset K such that translates of that compact subset under the group action cover the whole space. And the action is proper if for every compact subset K, there are only finitely many translates of K that intersect K under the group action. And there are lots of familiar examples appearing in sort of geometry and topology. So if we have the fundamental group of a closed hyperbolic surface, then we equip the surface with a hyperbolic metric, then the fundamental group acts isometrically on the universal cover, which is the hyperbolic plane. So the hyperbolic plane is a model geometry of the fundamental group of a closed surface. And the free group of rank 2 has a model geometry that's the 4-valent tree. And more generally, there's sort of universal construction that for any group gamma, if you take the Cayley graph with respect to some finite generating set, you get a model geometry that's that Cayley graph. So every finitely generated group has some model geometry that's a locally finite graph. And what we're interested in is seeing to what extent or which finitely generated groups have the property that all of their model geometries up to some relation, which I'll talk about now, are locally finite graphs. Okay, so in order to state the main problem I'm going to be talking about, I need to introduce the notion of domination of metric spaces. And the key fact that we're going to use is if we have a metric space, we don't just want to study the geometry of the metric space, but we want to study the algebra of its isometry group. So if we have a proper metric space, then properness gives you that the isometry group of that space is a locally compact topological group when you equip the isometry group with the compact open topology, or in this case, that's equivalent to the pointwise convergence topology. So, if we have two model geometries, X and Y, we say that X is dominated by Y if there is a homomorphism phi from X to Y, which is proper. So proper means inverse images of compact sets are compact, continuous, and the image is co-compact. And if you're not used to thinking about these things, notice that phi is essentially an isomorphism, a topological isomorphism up to compact error. Okay, the kernel of phi is compact and the image is co-compact. So it sort of covers isom y up to compact error. And the right way of thinking about this, sort of the informal way of interpreting this, is that if X is dominated by Y, then you can think of Y as more symmetric or possibly just as symmetric as the original space X is. And I'm going to illustrate this point of view with an example. So here we have torus X, And we can equip it with the flat metric. And at one point in the torus, we attach two antennae. We attach two unit intervals to that point. And we look at the universal cover, x tilde, and we get this metric space here, which is a copy of the Euclidean plane, where every point in the integer lattice, we have this pair of antennae attached. We have a pair of unit intervals attached. And we can study the isometry group of x tilde. And the first thing we notice is that x tilde is the Euclidean plane with some stuff attached, and every isometry of x tilde preserves that Euclidean plane. So by looking at the restriction of an isometry to the Euclidean plane, we get a map phi from isom x tilde to the isometry group of the Euclidean plane. And this map phi will satisfy the properties that are needed for domination. So x tilde will be dominated by e squared. And I just want to use this example to say why e squared, the Euclidean plane, should be thought of as more symmetric than x tilde. So firstly, let's look at the kernel of the map phi. It does have a non-trivial kernel. There are isometries of x tilde which induce trivial isometries of the Euclidean plane, namely an isometry that fixes the plane, but then might permute these, might sort of flip these these unit length intervals attached to points. So we can have an isometry that fixes the plane, but flips these two edges, flips these two edges, and it could flip infinitely many edges. And those isometries that are in the kernel are not very interesting because, for example, they have finite distance from the identity in the supremum norm. They're sort of compact noise in the isometry group, and they all live inside some compact normal subgroup, and there's not really any loss of information by getting rid of them and ignoring them. So this map phi, even though it's not injective, the kernel is quite boring. It's a sort of compact noise, and we don't really lose anything by getting rid of it. On the other hand, phi isn't surjective, and there are a lot of interesting isometries in isom e squared that don't come from isometries of x tilde. And one way of seeing this is that the image of phi has to preserve the integer lattice in e squared. And in particular, that means it's a countable discrete subgroup of the full isometry group. But the full isometry group is an uncountable, virtually connected Lie group. It's much bigger. There are lots of isometries of e squared that don't preserve the integer lattice. So we like to think of the Euclidean plane as more symmetric or better model geometry than x tilde. So here we have an example of model geometry of the fundamental group of the torus, z squared, which is dominated by the Euclidean plane. And the main problem that I'm going to talk about today and going to give a complete solution for is to find out, classify which finitely generated groups have the property that all possible model geometries of that group are dominated by a locally finite graph. So the example we saw in the previous slide, we have a model geometry that's not a locally finite graph, that's the full Euclidean plane, and we're asking for which finitely generated groups have the property that all of the model geometries are dominated by locally finite graphs. And an example of a model geometry that's not dominated by a locally finite graph is either the Euclidean plane or the hyperbolic plane. And you might think, okay, these aren't locally finite graphs, but maybe you can dominate these by some locally finite graphs in some clever way. Maybe there's some interesting, weird locally finite graph that you can come up with, which does dominate these spaces. And the answer is no, you can't. And that's a consequence of this proposition, which is fairly straightforward. I'll talk about the proof in a minute. So a model geometry X is dominated by a locally finite graph precisely if its isometry group is compact by totally disconnected. Okay, so we use the topology of the isometry group to say when X is dominated by a locally finite graph. And one direction is fairly straightforward. So the automorphism group of a locally finite graph is compact by totally disconnected, and that implies the forward direction. And the reverse direction is a little bit harder, but still not too bad. if we have a locally compact group, isom X, which is compact by totally disconnected, and is also compactly generated, which isom X is, then it's dominated by a locally finite graph called its Cayley-Abels graph. And this is something that you can construct using the algebra of isom X. Namely, you pick a compact open subgroup of isom X, which always exists by something called Van Danzig's lemma, and you can build a graph by taking cosets of this compact open subgroup and joining these cosets by edges in a certain way, so you get a locally finite graph. And this is a fairly classical idea going back to the 70s work of Abels. And it also generalizes the Cayley graph if isom X is an actual discrete group. Okay, and the problem I mentioned in the previous slide, about working out which finitely generated groups have the property that model geometry is dominated by locally finite graphs, it can be reformulated in terms of understanding lattice embeddings of a finitely generated group. So if we have a locally compact group, a uniform lattice in G is a discrete co-compact subgroup of G. And the key example is that if gamma is a finitely generated group and X is a model geometry of gamma, then after possibly quotienting out by a finite normal subgroup, which is the kernel of the action, then gamma is a uniform lattice in the isometry group of X. And we can now state a proposition which states how the problem on the previous slide is equivalent to understanding uniform lattice embeddings of gamma. So if we have a finitely generated group gamma, then it has a model geometry which is not dominated by a locally finite graph, if and only if, modulo some finite normal subgroup, the group gamma is a uniform lattice in some locally compact group that's not compact by totally disconnected. Okay, so if you're not comfortable with being dominated by a locally finite graph, but like uniform lattices in locally compact groups, then we can reformulate the main problem in terms of lattices. And I'll freely use this proposition throughout this talk and the proof of it to switch between the two points of view. Okay. So now we come to a slightly more interesting example of a group with an interesting model geometry, which is neither locally finite graph, nor is it dominated by a locally finite graph, but also isn't dominated by a homogeneous space, a sort of homogeneous manifold whose isometry group is a Lie group. So we consider this group the Baumschlag-Solitar group BS12, and that's a group with this presentation, generators A and T, and the relation TA T inverse is equal to A squared. And geometrically, this has a Cayley complex that I've got a picture of here. So this is the universal cover of the presentation complex of BS12 corresponding to this presentation that I've got here. And this, I mean, I've only got a portion of it here, but this is a model geometry of the Baumschlag-Solitar group BS12. And we want to give this a metric in the following way. So if we look at sort of a vertical line in the tree direction, so I forgot to say this model geometry, this topologically is the product of a tree and the real line, but metrically it is not a direct product of those two spaces, but it has topologically it's a product. And what we want to do is for every vertical line in this tree direction, and we take the product with the horizontal direction, and we get a sheet of this model geometry. And if we look at the cell structure here, we have something that looks a bit like the hyperbolic plane. The picture is the wrong way around. It's sort of like the lower half plane model of the hyperbolic plane. And we want to give this space X a metric such that each horizontal strip So the strip between two horizontal red lines is isometric to a region of the hyperbolic plane between two concentric horocircles. And we can do this in such a way such that BS12 acts isometrically on this space X. And notice I'm considering X as a metric space, and I'm forgetting about the cell structure on X. So I'm not assuming that isometries of X preserve the cell structure, and they don't in fact. And the key point is that this space X is not dominated by a locally finite graph. And we can do this either by calculating the isometry group, and the key fact is that we have isometries that fix the tree direction. You know, they don't flip any branches of the tree or anything, but they correspond to translations in the horizontal direction. So translations in the red line, along one of the red lines. And the point is we can have translations in the horizontal direction of arbitrarily small size. And we have a continuous one parameter family of translations in the horizontal direction. And that means that the isometry group of this space won't be totally disconnected and won't even be compact by totally disconnected. And so by the proposition we just saw, that means that this model geometry X is not dominated by a locally finite graph. And moreover, because there's a tree direction, the isometry group of this isn't a connected or even virtually connected group. It's something which displays a mixture of continuous or discrete type behavior, continuous type behavior coming from translations in the horizontal direction, and discrete type behavior coming from automorphisms of the tree direction. And that makes it an interesting group to study. And like I said, it's the first example we've seen of a model geometry which is neither totally disconnected, nor is it virtually connected. And in order to motivate the main theorem, we want to see what algebraic property of the Baum-Slug-Solitar group causes this model geometry to, or allows this model geometry to exist. And want to characterize when we can construct model geometries using some algebraic property of this group BS12. Okay. And this algebraic property is the notion of a commensurated subgroup. So if we have a group gamma and a subgroup lambda, we say that lambda is commensurated if for every conjugate of lambda within gamma, when we intersect that conjugate with lambda, that intersection has finite index in lambda. And the most obvious example is if lambda is actually a normal subgroup of gamma, then clearly it's commensurated because every conjugate of lambda is equal to lambda. But that's a very boring example of a commensurated subgroup. And this is a much more interesting example. It's the Baum-Slug-Solitar group, BS12, that we just saw. And the infinite cyclic subgroup generated by A is a commensurated subgroup. And you can see that it's commensurated using the relation. So the first thing to say is that if we conjugate this subgroup by A or any power of A, then we don't change the subgroup. And if we conjugate by T or any power of T, this relation here tells us we'll get some subgroup which is either a finite index subgroup of lambda or contains lambda as a finite index subgroup. And so this is an example of a commensurated subgroup that is not normal and is very far from being normal. So it can't even be made normal by passing to finite index subgroups or something like that. And another important example, which again is very related to some of the ideas we have seen and will see in this talk, is that if we have a locally compactly generated group G, then if it contains a compact open subgroup H, then that compact open subgroup H is automatically commensurated. And this is a fairly elementary topological argument. The idea is if we intersect H with any conjugate, then we get an open subgroup. And because that's an open subgroup of H, and because H is compact, only finitely many cosets of that intersection cover H. And so that means every conjugate of H is actually commensurable to H. And so H is a commensurated subgroup. And another very important example, which again is very related to the ideas in this talk, is that if a group G acts on a locally finite graph X, and V is a vertex of X, then the stabilizer of a vertex is always a commensurated subgroup. And this is actually, in some sense, a universal example, in the sense that if you have a commensurated subgroup, you can always construct a locally finite graph where the stabilizer of a vertex is that commensurated subgroup. So somehow 4 is the universal example in the sense that you can always construct a locally finite graph satisfying hypotheses from a commensurated subgroup. And in order to talk about the main result, we need a slightly more refined notion than just a commensurated subgroup. We need something called a uniformly commensurated subgroup. And to motivate this, the definition is a bit technical, so I'm going to talk about, sort of explain some of the terms in the definition before I get to it. So to motivate it, if lambda is actually a normal subgroup of gamma, then the action of gamma on lambda by conjugation induces a homomorphism from gamma to the automorphism group of lambda. And the question now is, if we have a commensurated subgroup, which isn't necessarily normal, then what's the analogous statement? And the action of gamma doesn't act on lambda by conjugation, but it acts on all finite index subgroups of lambda by conjugation, or it acts on all subgroups commensurable to lambda by conjugation. And this action induces a map gamma to something called the abstract commensurator group of lambda. And again, this might not be familiar to everyone. So definition of this abstract commensurator group, it's the group of all equivalence classes of isomorphisms between finite index subgroups of lambda. And two such isomorphisms are said to be equivalent if they agree on some further finite index subgroup. And a good example of this, a classical example, is that the abstract commensurator of z to the n is glnq. And this isn't too hard to show. The idea is that if you have an isomorphism between finite index subgroups of z to the n, then you can represent this by a matrix of z to the n, where the matrix is an element of glnq. That's sort of the basic idea. You have to sort of multiply by some rational numbers first to pass to some finite index subgroup, then you apply an element of SLNZ, and then you again multiply again by some rational matrix to complete the map. And if the group lambda happens to be finitely generated, which it will in the cases we're considering, then there's a natural injective map from the abstract commensurator group of lambda to the quasi-isometry group of lambda. So the quasi-isometry group of lambda is the set of all self-quasi-isometries of lambda, where two quasi-isometries are equivalent if they have finite distance in the supremum norm. Okay, and now we can state this definition of what it means to be uniformly commensurated. Again, this is a little bit technical, and if you haven't thought about these things, maybe a little bit harder to understand, but I'll give some examples in a minute. So if we have a subgroup, a finitely generated commensurated subgroup lambda of gamma, then we say that it's uniformly commensurated if the image of the composition, so we have a map from gamma to the abstract commensurator of lambda, and then we have a map from the abstract commensurator to the quasi-isometry group, and we want the image of this composition to be what's called a uniform subgroup of the quasi-isometry group. And this means that every element in the image Remember, elements in the quasi-symmetry group are equivalence classes of quasi-symmetries, and the condition is that we want every element can be represented by a quasi-symmetry with uniform constants, uniform as we pick elements in the image. And like I said, this is a little bit technical, so I'll give some examples. So here's the same definition we just saw. So first example is if lambda is a central subgroup of gamma, then it's uniformly commensurated. And this is easy to see because the action of gamma on lambda by conjugation is trivial. So that means every element in the image of this composition up here can be represented by the identity, and so it's clearly uniformly commensurated. The infinite cyclic commensurated subgroup of the Bamsel-Solitar group that we just saw is a commensurated subgroup that's not uniformly commensurated. And the way to see this is that if we conjugate A by a large power of T, the action will take A to a higher power of A, and so it will induce a quasi-symmetry with larger and larger constants. And we can get the constants to be as large as we want by taking larger and larger powers of T. So this is a commensurated subgroup that's not uniformly commensurated. If we have a commensurated subgroup which satisfies Moster rigidity, by which I mean it's a lattice in a semi-simple Lie group to which Moster rigidity applies, which is most of them, then it's automatically uniformly commensurated. So as soon as it's commensurated, it's always uniformly commensurated. And this is not hard to see because the idea is Moster rigidity tells you that every commensuration of the subgroup lambda is induced by an element of the Lie group in which lambda is a lattice, or if you prefer thinking geometrically, every commensuration is induced by an isometry of the associated symmetric space. So the point is the action of gamma on lambda by conjugation somehow doesn't distort things too much, and that the action doesn't give quasi-symmetries with worse and worse constants. And an example where this fails is if we have a closed hyperbolic surface and we have a pseudo-Lomonosov homeomorphism of that surface, and we consider the group gamma, which is the semi-direct product of pi1s with Z, where Z acts on pi1s by the map induced by the pseudo-Lomonosov. Well, this group gamma is the fundamental group of mapping torus of F. And we claim that the normal subgroup, pi1s, is normal, but is, in particular, is commensurated, but is not uniformly commensurated. Okay, and why is this? I mean, the idea informally is that if you take larger and larger powers of a pseudo-Lomonosov, then that will distort things a lot and will give quasi-symmetries with worse and worse constants. And so that means that this subgroup will be commensurated but not uniformly commensurated. Okay, so that's the technical definition we need. And now we can talk about the main theorem. And again, this completely solves the problem of classifying which finitely generated groups gamma have the property that they have some model geometry that's not dominated by a locally finite graph. Or informally, it sort of acts on some metric space where there's some continuous one parameter family of isometries, which that means it can't, those isometries can't arise as isometries of a locally finite graph. And the theorem says we have that. Gamma has a model geometry not dominated by a locally finite graph, precisely if gamma contains an infinite commensurated subgroup lambda, such that one of the following two things hold. So the first thing is lambda is a finite rank free abelian group. No extra conditions are needed. As soon as you have a finite rank free abelian, that gives you a model geometry not dominated by a locally finite graph. And the second condition the second, not condition, the second this alternative is that modulo some finite normal subgroup, lambda is a uniform lattice in a semi-simple Lie group, connected center-free semi-simple Lie group, and moreover, we assume that lambda is uniformly commensurated. Okay, so it's not just enough to have a commensurated subgroup that's a lattice in a semi-simple Lie group, but it has to be uniformly commensurated as well. And as I mentioned earlier, if lambda satisfies Mosto rigidity, which happens for most of the for most commensurated subgroups in 2, essentially the only exceptions are when lambda is a surface group, or when it splits as a direct product, where one of the direct product factors is a surface group. So if that doesn't happen, then lambda satisfies Mosto rigidity, and so by the example I had on the previous slide, that means it's uniformly commensurated. And another thing to say is that the main theorem also characterizes the class of finitely generated groups gamma, such that gamma is a uniform lattice in a locally compact group that's not compact by totally disconnected. So this, I mentioned earlier, that the 2 problems of finding model geometries not dominated by locally finite graphs and finding uniform lattice embeddings where the locally compact group is not compact by totally disconnected, these 2 things are equivalent. Okay. Any questions about the statement of the main theorem?
Yes. Natural question is for the second part. Which semi-simple Lie groups has uniform lattice that is uniformly commensurated?
Which what? Sorry, which?
Which semi-simple Lie groups that admit a uniform lattice?
Sorry, I stated it incorrectly. Okay, sorry. So we don't want. Sorry, we want lambda to be uniformly commensurated in gamma, but not in a semi-simple Lie group. Sorry, I stated it ambiguously. We want lambda to be uniformly commensurated in gamma, and we don't care about whether it's uniformly commensurated in the semi-simple Lie group. So yeah, thanks. Sorry, thanks for clarifying. Does that help?
Yeah, you still have a question. Which semi-simple Lie group has a uniform lattice that is uniformly commensurated in some group gamma?
I mean, I think it generally. I mean, they always would if it satisfies.
Or you can always take a gamma to be lambda.
Yeah.
Okay, that doesn't make sense.
Yeah.
Okay. Thanks.
Yeah, so sorry, I stated the main theorem ambiguously. We want lambda to be uniformly commensurated in gamma, and also a lattice in a semi-simple Lie group. Okay, so we can be a bit more concrete than this. I mean, this is rather than working with all finitely generated groups, we can restrict to groups of cohomological dimension 2, and then we can precisely say what the class of groups is. So a generalized Bam-Slug-Solitar group, by definition, is the fundamental group of a finite graph of infinite cyclic groups. So the Bam-Slug-Solitar group that we saw earlier, BS1-2, that is an example of a generalized Bam-Slug-Solitar group. But this is a much wider class of groups, and they've been fairly extensively studied and have lots of interesting properties. And we have the following corollary to the main theorem. So if a finitely generated group gamma has cohomological dimension 2 and has a model geometry that's not dominated by a locally finite graph, then one of the following 2 things happen. Either gamma is a surface group, by which I mean the fundamental group of a closed surface of non-positive Euler characteristic, or gamma is a generalized bound subsolitary group. And like I said, these are groups that can be described very explicitly. They have lots of nice properties. And moreover, in both of these cases, we can actually describe all model geometries of these groups, namely generalized bound subsolitary groups have model geometries that look a bit, that topologically look like a tree times the real line. They look a bit similar to the model geometry we saw for BS1-2 earlier. And surface groups obviously have model geometries dominated by, or model geometries that are the Euclidean plane and the hyperbolic plane. And these are sort of the best model geometries in the sense that any other model geometry of these two groups is dominated by one of those sort of canonical model geometries. So this is very nice. It gives us explicit description of the class of groups of cohomological dimension 2, which have some model geometry not dominated by a locally finite graph. Or in other words, when you want to study them geometrically, they have some aspects of sort of continuous type behavior or some directions where there's a continuous one parameter family of isometries. And the main tool that's used to deduce this from the main theorem is the following theorem of mine, which generalizes work of Krupp-Holler. And in fact, Krupp-Holler's theorem is actually enough to deduce this corollary, but the theorem I'm stating is more powerful. So if we have a group gamma and a subgroup lambda, which is commensurated, such that both lambda and gamma are of type VFP, so this is a finiteness property, then if the cohomological dimension of gamma is strictly one more than the cohomological dimension of lambda, then gamma splits as a finite graph of groups where all the vertex and edge groups are commensurable to lambda. And the idea, how you deduce the corollary, is that we have this group gamma here, and it has some model geometry that's not dominated by a locally finite graph. And what we now want to do is to analyze the cases and see what possible commensurated subgroups lambda can be commensurated subgroups of gamma. And essentially we reduce to the case where lambda is infinite cyclic, in which case we can apply this theorem to deduce that gamma is a generalized bound solitary group. Or if gamma contains a commensurated subgroup that's not infinite cyclic, then you can show that the commensurated subgroup has to actually be a finite index subgroup, and then the group gamma has to be the fundamental group of a surface. Okay, so that's the corollary. And now I want to talk a little bit about some of the ideas that go into the proof of the main theorem. So the forward direction is both the easiest direction and the harder direction. It's easier because it follows more readily from results in the literature, but it's harder because the theorems it uses are quite sophisticated and hard. So the forward direction is we fix some finely generated group gamma, and it has some model geometry X that's not dominated by a locally finite graph, and we want to show that it has a suitable commensurated subgroup lambda. So what's the idea? So we let G be the isometry group of this model geometry X, and we let G0 be the identity component of the isometry group. And because of the assumption that X is not dominated by a locally finite graph, that tells us the identity component has to not be, can't be compact. And we'll use this to show that gamma has the commensurated subgroup lambda, which satisfies the hypotheses of the theorem. So by a result of Gleason Yamabe, and this is the work that went into showing Hilbert's fifth problem has a positive solution. After possibly quotienting by a compact normal subgroup, we can assume that G0, the identity component of G, is a connected Lie group. And this is a very hard theorem to prove. It's very lots of machinery that goes into this. And now there are two cases to consider. So if G0 has compact radical, remember the radical of a Lie group is the largest connected solvable normal subgroup. If the radical is compact, then up to compact error, the group G0 is semi-simple. And in this case, we can show that the group gamma contains a subgroup lambda, which is commensurated and is a lattice in G0. And moreover, because the outer automorphism group of semi-simple Lie group is finite, that tells us that the commensurated subgroup lambda has to actually be uniformly commensurated. And the second case is when G0 has a non-compact radical. And this means, again, up to compact error, possibly, up to sort of quotienting out by some compact normal subgroup. G0 contains some characteristic subgroup isomorphic to R to the n, essentially because G0 has a characteristic solvable subgroup. You take the last term in the derived series, and that will be 3 abelian group. Sorry, not 3 abelian. That will be isomorphic to R to the n for some n. And again, we use this to show that gamma has a commensurated Z to the n subgroup. So again, there's a bit of work in these two cases, but this is the outline and the main tools, the work of Gleason and Mabe, a little bit of stuff about sort of totally disconnected locally compact groups, and some Lie theory to say, for instance, to reduce the two cases and then deduce that gamma has the commensurated subgroup that we want to prove the main theorem. So that's the direction which is uses more machinery but is easier to prove. And the other direction, we want to start with a finitely generated group containing some commensurated subgroup, and from that we want to build some locally compact group containing that group as a uniform lattice. And I'm going to restrict to a special case which illustrates the general ideas and the strategy, even though it's a little bit simplified. And the special case is the following proposition. So if gamma is finitely generated and it contains a commensurated commensurated infinite cyclic subgroup, then there is some locally compact group in which gamma is a uniform lattice, and that locally compact group is not compact by totally disconnected. So we want to build some locally compact group that's not compact by totally disconnected. And by one of the propositions I stated near the beginning of the talk, this is the same thing as constructing, or this is equivalent to constructing some model geometry that's not dominated by a locally finite graph. Okay. So let's first split to a very specialized to a very restrictive case, namely where gamma splits the direct product, where one of the factors is the commensurated subgroup lambda, which in this case is normal, and the other factor is the quotient. And in this case, it's very easy because gamma is a direct product of Z times Q, where Q is the quotient. And so we can just embed gamma as a uniform lattice in R times Q, and R is connected. So gamma is a lattice in some locally compact group that's not compact by totally disconnected. And in the general case, we want to somehow mimic this argument, but it's much harder because we don't actually have a direct product. We have to do a lot more work, but we mimic it in the sense that we want to embed gamma as a uniform lattice in some locally compact group G, where G fits into the short exact sequence 1 R, this short exact sequence here, where the kernel is R and the quotient is some group Q. Q won't be the quotient of gamma by lambda. I mean, lambda's commensurated and not necessarily normal, but it will contain the same sort of information that the quotient does. And in particular, in the case where gamma actually does split as a direct product, then this short exact sequence here will also split as a direct product. So there are, the first step of this is to construct an action of gamma on R. And the idea is gamma acts on, or gamma commensurates some infinite cyclic subgroup. And we somehow want to use this and use the action by conjugation on groups commensurable to lambda to construct some action on the real line. Then we want to construct some group Q, which corresponds to some sort of completion of the action of gamma on the cosets of lambda. I'll say a little bit more about that in a minute. And the last step is to construct the extension G using cohomology. So we want to construct some continuous cycle from H2Q in H2QR, and this defines the group G, which fits into this short exact sequence, and then you can show that gamma sits the uniform lattice in this group G. And step 3 is a little bit technical, and I'm not going to say anything more about that, but I'll just briefly elaborate on what goes into steps 1 and 2. So for step 1, recall we have a finitely generated group gamma, and it contains a commensurated subgroup, infinite cyclic subgroup lambda. And let's assume lambda is generated by some element A. And because this subgroup is commensurated, for every element G of gamma, there are some non-zero integers n and m, such that G a to the n G inverse is equal to a to the m. And we can now define an action of gamma on the real line, where G acts, if we have G as above, then it acts by multiplication by m over n. And even though m over n is not, even though m and n aren't necessarily well defined, the ratio m over n is well defined, and this does give a genuine action. And somehow the right way to think of this action is that because lambda is commensurated, gamma won't necessarily act on lambda by automorphisms, but we can somehow use the action of gamma on groups commensurable to lambda to construct this action on R, which mimics the action of gamma on lambda. And the second step is to construct this group Q by, in some sense, completing the action of gamma on the cosets of lambda. So how does this work? So we can build a graph X where the vertices are the left cosets of lambda, and the edge sets are, well, G lambda and we connect to two cosets by an edge if they differ by a generator in the following sense. So G lambda is connected to G S lambda by an edge, and S is any finite generating set of gamma. And you can do this for any subgroup. It won't necessarily be not necessarily a commensurated subgroup, but if the subgroup is commensurated, then this graph X is locally finite. And in fact, this is an if and only if. If the graph X constructed here is locally finite, then that implies lambda has to be commensurated. And that's a fairly easy exercise. And now what we do is we have an action of gamma on this graph X. It's a connected locally finite graph X. And that gives a homomorphism from gamma to the automorphism group of X. And if we take the closure of the image in the automorphism group, then this gives us some locally compact group Q, and that's called the Schlichting completion of gamma with respect to lambda. And notice that if lambda is actually a normal subgroup of gamma, then this Schlichting completion is actually the quotient group. So somehow this is a surrogate for the quotient group if we only have a commensurated subgroup and there isn't a normal subgroup. And then step 3, which is a little bit too technical to say anything more about, is we somehow want to build, or I'll go back to the previous slide, we want to build this short exact sequence, this group G that fits into this short exact sequence using the action of gamma on R and using this group Q that we just defined. And this is done using some co-cycle. So I think I'm out of time. So I had some extra stuff, but I won't talk about that. So thanks very much for listening. Let me know if you have any questions.
Let's thank Alex. Any questions?